Great. So, welcome folks in the lobby. Thank you very much for dialing in today. Welcome to Design Leaders in Tech, a new speaker series from the Student Design Hub. The goal of this series is to have local leaders from our tech industry here in Newfoundland and Labrador come in and discuss how they approach problem solving and developing products. So before we kick off the discussion, here's a couple things that I wanted to mention. You might notice that you can't see other people in the WebEx. You're not alone out there. WebEx events, which is different from meetings, disables the chat function. So instead we have this Q&A bar on the right. So if you have any questions throughout the presentation, please put them in the Q&A box. We can see them, and I'm going to keep track of them throughout the presentation. We'll make sure to answer as many of your questions as we can as we go through. And they'll pop up publicly to everybody after we mark them as resolved. So if you'd like to ask our presenter a question directly, just make a note in your question that says, I would like to be seen, or please let me speak. And then we can promote you to a panelist, and then your webcam will come on and you can verbally ask us the question. So if you're having any technical difficulties at all, please let us know. Just shoot me a message in the Q&A, and we'll get you straight in the way. So without any further delay, I'm excited to hand it off to Mariana Golden, a mechanical designer at DuXion Motors.
All right. So I think right now you're the presenter. So okay, there we go. All right. Can you see my screen there?
Yeah, we sure can.
And is that showing you the full screen, or?
We're still getting your tabs at the top. But it is full screen.
Okay, I don't know if it's a particular setting on WebEx.
I think you should be good. All we can see is, you know, the Google or your tabs at the top of Chrome. So.
Okay, gotcha. All right, so hi everyone, I'm Mariana Golden, and I'm a mechanical designer at DuXion Motors, and this presentation is on how a student team taught me that success requires you to plan for failure, and specifically multiple failures throughout the course of the design process. So Paradigm Hyperloop was the student team that I was on. I was actually on the Northeastern side of the team. It was an international collaboration of students from MUN, Kona, and Northeastern, and that was for the SpaceX Hyperloop Competition. The team participated in Competition 2 and Competition 4, but I'm mostly going to be talking about Competition 4. I'll let you know if I'm using examples from Competition 2. The goal of the competition was to brace high-speed pods in the SpaceX Hypertube. And for Competition 4, we were using an electric propulsion system. I was on the team for 2.5 years. That was for Competitions 2, 3, and 4, but we didn't actually compete in Competition 3. Now I'm working at DuXion Motors, which is an advanced motor design and manufacturing company developing electric propulsion systems, and right now that's for marine and aerospace applications. It was founded in 2017, and since then there have been actually a lot of members of Paradigm on the team, or let's see, there we go. So from here, I'm just going to go through different parts of the design process, or that cycle of design, build, test, and talk about basically lessons learned at each stage, which is basically where we messed up on the team and what we learned from that. But if you're no matter what team or company you're with on an engineering project, you're going to run into these 3 stages and repeat them over and over again until you get from design concept to prototype to final product. None of these stages are linear, but I've just outlined basically steps that you end up going through during the design phase, and I've done this for testing and building as well. So one thing that's actually really important that gets forgotten more than people would think is defining project goals clearly as your first step, because sometimes people will have a different vision for the team, and if you aren't clearly aligned on them, that can actually affect product topology, which makes it really hard to design if you're designing things with different goals in mind. So examples of how that can affect project goal can affect topology is, so we had the competition 2 pod, and that was actually designed for levitation because that's what that competition had. There was kind of 2 separate streams, whereas competition 4 was solely focused on top speed. However, we decided to focus more on scalability for an actual Hyperloop concept. So we were using a motor that's a bit more realistic. It was an EV conversion motor, or a motor commonly used for that application. Whereas the winning team for multiple years, TUM, they used to be called BAR, a German team, would always make really small pods with teeny tiny motors so that it was super light. And basically that decreased their braking force and made it a lot easier for them to safely get to top speed and stop. But that was basically like, those are 2 very valid ways to approach it. It was just decisions that each of those teams had to make. And at DuXion, it's actually also really important for us to define project goals clearly because we have multiple different projects with different goals. So one of our projects is the electric jet, which is a turbofan replacement, and that's designed for maximum thrust to weight ratio. This design uses more novel manufacturing processes and custom components. So it'll use additive manufacturing, and it's not designed to be manufactured cheaply, essentially, whereas the marine motors we're designing are designed to use more off-the-shelf components so that we can design them quickly and manufacture them quickly. So once you define your project goal, the next 2 steps really are to define your topology and define your key parameters. So from here on out, I'm going to mostly be using Hyperloop as an example. So this is a picture or screenshot of the Hyperloop. It's a page from the rules and regulations, and that gave us a cross-section view of the SpaceX Hypertube. And that used an I-beam, which we clamped to for propulsion. So we're not riding on a track. It was clamping to an I-beam. And they had keep-out zones for braking for safety reasons. And it's important when you get key parameters, there's really 2 types of design constraints you have to design around. There's fixed parameters, which are basically I-beam dimensions, tube length in this case, basically environmental variables that you can't control and you have to design around. And then target parameters that you define, such as, in this case, mass, top speed, and pod length. And those are basically variables to target within reason. So we would always have a spreadsheet full of calculations, and basically that was good for team record keeping, and also it was really easy to plug numbers in and try things out for different when we were trying to source different components. And then the next step that we that I would recommend from there is to source critical components before you get into the meat of the design. A critical component is basically anything that's off the shelf but has a long lead time and might need custom modifications, but it's essential to the design. So basically a part that you design other parts around. So on the pod, that would have been the motor, inverter, shocks, some of the bearings that were hard to source, pulleys and belts. We ended up sourcing the belt too late and had to do a lot of scrambling and redesign since it was a lot wider than we had designed for. Components that aren't off the shelf but need to be custom manufactured and have a long lead time might also be critical. So in that case, that might have been the inverter enclosure because it was made of carbon fiber, and that has a really lengthy, involved manufacturing process. The wheels were also critical because they needed to be machined, coated, and then balanced. And the motor needed an adapter to connect to one of the pulleys because the output shaft was splined. So watch out for couplings because they can actually be a long lead item that you might not think of. And items such as, like in our case, it was the drive shaft, but if stuff needs an extra operation on top of just machining, like our drive shaft needed to be hardened, that can also take a long time. Locking these components will give you critical dimensions that you can use for detailed design. And don't be afraid to ask manufacturers for spec sheets or CAD models. A lot of them will give them to you, especially if you say you're on a student team. And if you can't find them, check GrabCAD because I found like entire turbine assemblies on there, and like I found an entire lobster boat. It's sick. And then also start a bill of materials early because it's way easier to do it as you go instead of working backwards. Once you source your critical components, you can go into the detailed design phase. So that's where you get into detailed component design, where you're designing basically things like brackets, mounts, framing that are being designed around the critical components that you're not getting manufactured custom. And these components more typically can be made with traditional machining operations in your standard shop, like the MUN shop. So kind of mill, lathe, CNC laser cutter, water jet, etc. These are the components that you'll be designing around, or that you'll be designing around the critical components. And make sure when you're doing this to start sourcing fasteners, like not just using, if you're using SolidWorks, not using their smart fastener thing, but actually going and physically sourcing those fasteners. Because that'll make it a lot easier in the long run, so it's not an extra step you're doing on top, and also to make sure that they actually exist. And while you're doing this, make sure everything meets the factor of safety for whatever standing you're designing for. Because we definitely made some mistakes on that end, and that can really be a showstopper. So this was an FEA study performed on a competition 4 chassis, and it had several issues such as loads applied as different point loads versus distributed loads from the wrong angle, etc. And a lot of these happened because we were trying to simplify the simulation. One tip for simulations is if you're trying to simplify something to make it easier to run, which is pretty common practice, especially for iterating, make one really detailed simulation with everything in it. Check that against hand calcs and check that against a simplified simulation, just to give yourself a sanity check, and then use the simplified simulation to iterate. We got roasted at SpaceX for this one, not only because the FEA didn't have the loads applied properly, but also because we did all the manufacturing drawings, but did not check with the manufacturer that they could hit the weld tolerance required. So that one made a lot of components not be able to fit, and also significantly reduced the yield strength of the aluminum because we didn't get it heat treated afterwards. So that's something to look out for. The chassis design was led by Connor Walrath, who worked at SpaceX and is now working at Tesla. And there's a few people that I mentioned in this presentation, and all of them have really cool jobs now. So that was a really great thing that the team did. This is an infamous mount block designed by my friend Rowan and me for the Competition 2 pod. And the issue with this component was that there's a lot of operations here, there's a lot of material, and it was not really designed with like the milling process in mind. It was physically machinable, but really difficult and really expensive and took a lot of stock. And one of the big challenges was that this is a through hole all the way through this entire block, meaning that you either need to pass a drill bit all the way through this entire thing, and once you get to the bottom of a hole that long, the drill bit will start to walk and mess up your tolerances. And I think what ended up happening was having to drill the hole from each side really carefully, which was tricky because there was a through rod connecting them both. But he later went on to become Rowan later became the competition 4 mechanical lead and is now an engineer at Breath Suite. And I show a mount that he designed for competition 4 that it's kind of the opposite of this. So once you get through the detailed design phase, you get into the building process, and by that I mean 75% of it is manufacturing and contacting manufacturers and getting into the shop. 15% of that is not losing all the parts you get, so organization, and 10% is actually building. When you're working on manufacturing drawings, don't forget tolerances and clearances. It's really easy, even if you know that it's a thing that's going to come up, to forget about them, because they're not something they're not a visual feature you can see. So if you already had a structural or mechanical design review and think you're ready for manufacturing, you're not. You should have a second design review, or you'll have multiple, but you should have one that's explicitly for manufacturing and goes over tolerances, clearances, and sometimes surface finishes and machining operations or manufacturing operations. Tolerances and clearances can also affect FEA results, so watch out for that. So this is another mount block designed by Rowan Meany, and this one is a really clean design. It was designed to be manufactured on a CNC machine. And since there were a ton of these teeny tiny brake housings, they were sent to an external manufacturer because it would have been tricky to do in-house, and they needed to be as light and thin as possible because there were so many of them, so that would have really added to the weight. So yeah, this was a really nice, like, once he manufactured these and we got the parts, they were supposed to have basically a sleeve fit into them, and you could just see the sleeve like slowly sink into them because they were really nicely tolerant. So that's how things should work out. And here's a really important note, and if you take anything from this presentation, I would say take this, which is that technicians, machinists, suppliers, and manufacturers are key. They're worth their weight in gold because engineers cover like a breadth of knowledge, which is mostly conceptual, and people on the manufacturing side have a really like depth of knowledge. Engineers tend to think that they're better or smarter sometimes than technicians, machinists, and suppliers, and that is not true. They have a very different skill set from you, and a lot of them have been in whatever field or craft they're in for their entire life. So they have, where engineers have a calculated knowledge of a lot of things, these people have an intuitive understanding based on years of experience. So they can really speed up the process for you. And this also comes in really handy down the line if you talk to a lot of manufacturers and machinists, because familiarity with manufacturing processes and relationships with manufacturers helps a lot with innovative design. A lot of innovations come from using an existing technology for a totally different purpose, and interacting with this kind of supply chain side of engineering will give you first of all, a mental inventory of what technologies exist and give you those connections for the future. So this is really, really important. And I think a lot of people take it for granted. And also it's really fun to talk to them about it. So kind of an example of this is we had an electronics enclosure that was supposed to seal a lot of the electronic components for pod 4 for vacuum, because a lot of them were not rated for that. And we had traditional O-ring gaskets and they wouldn't seal. There was a lot of leakage happening. So we ended up kind of getting desperate and walking to a rubber supplier shop, and they found us a closed-celled foam gasket and this lovely poem about rubber. And that's why it's fun to go into these places, because you never know what you're going to run into, and they're always like, they just have some characters there. It's really fun, and if you know how to talk to them, they get really excited and help you in a way that like design engineers don't. It's just a important perspective. This is another example of a design that I don't really think was feasible in the long term, but competition 2 used air skates that used a flexible material on the bottom in order to, like, it's basically a bag that inflated and lifted the wheels up off the ground slightly. And the material we ended up using for that bag was ripstop nylon, which is a waterproof material commonly used for parachutes. We used a sewing machine to puncture holes in the waterproof coating to let air escape and create a thin film of air under the skates to basically reduce friction between the bottom of the skate and the track. And they also used a thin mesh in the middle to diffuse the air to distribute it evenly, which is commonly used in filtering applications. So this particular design was not practical at high speeds. However, sewing machines and nylon fabrics are used in a lot of heavy-duty industrial applications because of nylon's high tensile strength. So it's a lot of things that you wouldn't think of. And then if you talk to a manufacturer or supplier, they'll just have these things that like probably don't come up in like your material sciences course, but are actually used in industry a lot. So after that, when you get onto the building stage, some suggestions are to maintain an organized bill of materials and use it as a checklist when you begin to receive them and take inventory. And that should include every fastener and fitting that you have. When you start getting your components, take inventory and mark off everything you get and everything that's late, because otherwise it seems like a lot of effort, but when you're sitting at the pile of hundreds of miscellaneous bolts and spend like 6 hours organizing them, you learn to make an organized bomb. A tip for sourcing fasteners is make master car, because it might not be the cheapest option and you might not actually order bolts from there. But if you use it as a fastener inventory, they have every kind of common fastener under the sun and some actually kind of cool ones. And you might find some types of fasteners and tooling you didn't even know existed. And then you can go and like look up that kind of fastener and see what exists on other sites. This is an example of one of my favorite tooling types that I just had no idea existed, and I was just throwing stuff into the search bar, but it's a reverse counterbore tool. So basically it has a separate shank and then the counterbore top slots into it. So you can put the shank into like a hole first and then tighten on the head and then pull the, well, you put the shank into the drill truck and then pull it backwards to counterbore the backside of the hole. And I don't know, a machinist might not love you if you walked in with that, but I mean, if you order it and figure out how to do it properly. It's cool to be able to find stuff like that and then search it up on websites that might be cheaper. And then once you get onto assembly, a couple lessons learned is mechies, don't forget that the electrical side of the team exists. Communicate with them and make sure that there are plans for mounting electrical routing, connectors, fittings, and stuff. Bend radius of wires is a big one that will get you. And it's sometimes hard to CAD that up or guess. So just take a worst case guess at least, so that you make sure that you have space there. Come up with assembly procedures beforehand and know if something's too heavy to safely lift, you need an assembly jig or like a gantry and loading straps and hooks, and that should be in your plan before you order all the components. And make sure there's enough clearance in terms of assembly for hands, tools, and fastening, and not just the bolt head. So this is our full pod for assembly. And then when you get onto the testing phase of the design process, test rigs and SOPs or safe operating procedures have a design and manufacturing scope all of their own to make sure to factor that into your project budget and timeline. Particularly fit checks are probably not going to go right the first time, especially if you have a prototype with a lot of different components, and the more components you have, the more tolerance stack up you have. So if you have a bunch of parts that are all connecting in different ways or have surfaces flush against each other, not only is it the individual tolerance from surface to surface, it's kind of the entire assembly tolerance stack up, so they can all affect each other. So if one is a little bit off, they'll all be a little bit off and nothing will fit. So there may be some flexibility needed, especially if you're having students machine parts for, like, try to machine parts a little bit oversized rather than undersized if you have to, just so that you have a little bit of material to take off just in case it doesn't fit. Or just at least double check everything multiple times with calipers and buy enough stock to make multiples. Yeah, so I kind of got into that already, but safety checks and fit checks come before any of the actual subsystem or full system testing. Make sure you have a safe operating procedure document written for each assembly and testing operation. So these will include hazards, including really basic things such as pinch points on mechanical assemblies, loose clothing or hair, and then might get into hazards such as, like, we had a lot of high voltage or high pressure systems depending on the nature of your project. Most of these SOPs were written by Jack Chapman, who's currently working at Hatch in Montreal. And sorry, just switching to the next slide here. So fit checks are pretty self-explanatory, but ours led to a huge amount of issues and rework. And that's something that you can try to mitigate beforehand, but really you should just build time into your project timeline to fix those if you need to, and also make sure to order extra stock, because there's definitely going to be, if students are machining stuff, there's going to be parts that get messed up at first. So to name a few examples, our suspension brackets were almost impossible to install because we had gas springs basically forcing this bracket up and into the shaft of the wheel, which pushed it down into the I-beam. And those were shipped fully extended, so not at their compressed length, and that made the bracket pretty much impossible to install. And then we had to use a gantry and lifting straps to lift the end of the pod so that we could fit those in and then compress the entire assembly afterwards, but we just completely missed that when we were ordering them. Our tensioner brackets didn't fit on the frame because of the weld beads on the frame. The tolerances were just like, not even like, oh, okay, a couple of thou off. It was like an entire millimeter of material added, and you can kind of see that in this picture here. Like these huge weld beads, and that was something that we should have talked to the manufacturer about beforehand, or like move the location of mounts so that they didn't interfere. Our upstop wheel mounts had incorrect hole locations, so we had to remachine them last minute. One of the keys in our drive shaft was installed incorrectly, and we lost that entire wheel assembly, but luckily we had an extra and we managed to salvage the bearings in that one. But we had to use spares, and like those were some very expensive parts. So yeah, that's something to also note, is if you know that something is supposed to be, like, know what type of fit it's supposed to be. So if it's not supposed to be a press fit, it should not be a press fit, because you'll lose stuff that way. Yeah, so this image in the middle is that bracket that the gas springs were going into, and the manufacturer actually welded these mounts on much too far apart, and that was something that they were used to welding, like big steel beams, so tiny tolerances didn't matter as much to them, and that was just not something we communicated well with them. And then these are the brake mounts, which were water jetted, and we had to we had to machine them down to size afterwards. And that was actually a really fun day because I just got to go into the shop and like machine everything down, and was pretty proud of this fit over here on the left. So then you get into subsystem testing and full system testing. Depending on the size of your prototype, you may have to break the testing down into mainly subsystem testing, and you might not get a chance to fully test it. Especially if it's like a vehicle or something, like you just might not be able to do that beforehand. So we, for Hyperloop, had a dynamic testing assembly, which I'm going to call the DTS from here on out. And testing is interesting because that's a whole other design scope, and like you'll have a part of your team working on the design of the actual prototype, and then you'll have a part of the team probably focused just on testing, because that may be just as big of a scope of design as the other stuff. So our test stand used a big disc of aluminum, approximately 3 inches by 20 inches in diameter, and that was spun up by an electric motor to match the kinetic energy of the pod traveling at 400 kilometers per hour. For brake testing, one of the brake modules was clamped onto a smaller rotating disc that shared the same shaft as the larger disc. And during testing, they successfully stopped the rotating disc assembly. So that was a huge success for our team. Definitely the testing operation that went the best for us, and that was a collaboration between Rowan Meany, who I mentioned earlier, and Gavin Burden, the testing lead, who's now working at Pangeo while completing his degree. And also, as a note, he did, I'm pretty sure, all of these renders. Yeah, so. The dynamic test stand was also used to test the propulsion system, and this time the pulleys, motor, and belt were assembled onto the test bench with a modified tensioner assembly. So that was basically so that we were applying the same amount of tension as we would be applying on the real pod to design spec. The other end of the belt was attached to the shaft of the DTS. And so this is where we ran into a lot of trouble, because the DTS, while we were running it, would start to vibrate violently, especially when we went up to full RPM and torque. And the belt would occasionally lose traction and start to slip, and like you'd hear it, like you'd hear the teeth on the belt grinding against the teeth on the pulley, and eventually it just snapped altogether. So we discovered what happened there after looking at video footage was the DTS assembly was vibrating violently and basically jolting itself around, and while that was happening, the shaft on the DTS shifted forward. So on the red line there, that's the shaft that shifted, and that meant that the pulleys were misaligned, and pulley alignment is extremely important, especially when you're using a belt because otherwise you're loading it improperly and it'll snap. So we fixed this issue by adding spacers to the assembly that I'm pretty sure Gavin like ran down to the shop to lathe. And yeah, there was a lot of last minute machining, which is, I mean, I'd say common for a student team. But you learn a lot that way, especially when the shop gets used to you being there and puts up with you. Shout out to Jerry, who I think is now retired, but he really helped us out. Yeah, so that issue was solved by spacers, and that was because the shaft was not properly restrained on one end. So there was a shaft collar there that was supposed to restrain it, but it wasn't doing its job properly. So basically a huge part of the engineering process is analysis of failure modes, which is kind of what I was talking about on the last slide. This is part of the process and not a what if. It's inevitable in your first prototype that things are going to go wrong. So just build time into your project timeline to allow for failures. For testing, proper sensor setup is super critical in being able to properly analyze failures. So, I mean, in our case, there were a lot of sensors built into the motor, and then we would have external sensors, both in like for the motor itself, but also in line if there's a pressurized system such as like braking. So that would have any sensors that you'd have in a pneumatic system like pressure, temperature. Temperature, sorry, got out of order there. Pressure transducers, temperature sensors, and like for our electronics enclosure, we had pressure transducers in line and in the enclosure itself. And there's like a really huge list there, and that also becomes there's not just the physical design of it, but there's also making sure that you have like a line that connects to the brake line or the electronics enclosure or vents or a port on the top with like an MPT fitting where you can fit in a pressure transducer or temperature sensor. So there's definitely always going to be more to that than you expect. And the more data you can get, the better you can analyze failures. There's a lot I couldn't even get into here because there were a lot of different subsystems on the pod. And video footage is also incredibly helpful in interpreting failures. And in a broader sense, failure really pushes people towards innovation because failure indicates that you're doing something that hasn't been done before. And if you're not failing, you're probably not innovating because you're doing something exactly to spec, to design, which means that it's been designed before. And I know this Student Design Center is really aiming for innovation. And also always remember safety first. Yeah, and that's the whole presentation. I know there were going to be some questions afterwards.
Awesome. Thank you so much, Mariana. So just a reminder to everybody who's in the audience, feel free to put your questions in the Q&A section, and we'll kind of read them out. And if you want to be seen, just let us know. Just say, hey, I'd like to ask my question in person. But to kick us off, I'll ask a question or two, and that'll give you guys some time to start thinking of questions for Mariana. So a bit of a generic one to start us off. Ari, what's your favorite part of being a designer at a small tech company?
I really like that it pushes me. I think with a lot of larger companies, you'll end up optimizing a single part over and over and over again. And we do that here because that's part of anything really. But I like that it pushes me to look at like the full system and the full assembly. And that's one thing that I really like is assembly modeling. because I think you get a really good sense of like the system as a whole, which I think can sometimes lead to better designs.
Awesome. So earlier in your presentation, you mentioned that not accounting for the bend radius on wiring might impact your designs.
Yes.
Want to elaborate on that a little bit?
Yeah, so on our electronics enclosure, we had, I mean, the inverter had these huge wires coming out of it, like, I mean, I think they were like, some of them were like an inch in diameter, the fitting itself, on the ID. And those have a massive bend radius, and like, you don't really think of wiring as like a component that's going to get in the way of other stuff, but then it does, and it sucks, and it definitely helps in terms of CAD to try to look up what's the vague bend radius of this wire and actually physically put the wire in there. And there are some wiring options in SolidWorks which are not great. Sometimes I'll just do it as like, okay, what is the wire bundle size? And then I just use that as a cylinder and extrude it as a spline and see if it physically fits and check the bend radius. And that's one thing, is using SolidWorks as like a measurement tool, or using it as a, like, you can use it so you assign like the mass of every component in the assembly and use that for a mass check. So definitely try to do as many physical checks as you can in the design part, and like use CAD as a tool.
That's really good feedback, and I don't think a lot of students think to, you know, completely do all of their assembly work in CAD, but, you know, take advantage of just the spatial characteristics of it, which is something
I would recommend, even like the way I ended up building assemblies, because I kind of managed the like assembly model for Pod 4, was I took individual subsystems and built them as a subsystem, and then put them as a subsystem into the full assembly, so that one, that makes your model a little bit less likely to crash, especially if you have a bunch of bolts and stuff. Also, another trick for that is suppressing threads. But if you assemble them that way, and also when you, the kind of the philosophy when you're setting up your subassembly CAD is assemble it or make stuff in a way that you would assemble it, because it's a really good sanity check. You can also use SolidWorks motion study if you don't have like a giant assembly, to do kind of a fit check. And there's also just maybe visually taking a look and seeing like, okay, is there clearance for this? Is there clearance for me to fit like a bolt head into it, or a fitting, or a wire, or, and can I actually physically like put it on the model in this way?
That's great. Thank you. Question from Dr. De Silva. He wants to know if it's okay to share this presentation with his class who are currently stuck on a midterm.
Oh yeah, for sure.
And he had a few questions. So, how did the weld joint analysis using FEM, or sorry, how was the weld joint analysis using finite element, or sorry, FEM done? Maybe I'm misreading that. How did the weld joint analysis using FEM? How was the weld? Sorry, Mariana, can you see the question? Maybe I'm just I'm a little bit of a.
I don't think I can see it.
Okay, let me send it to you. There you go. Might have popped up there.
Okay, there we go. Okay, so for the weld joint analysis, actually, like, we did not do this right, for the record. I would recommend, like, we were using SolidWorks for most of this analysis, but if you can use ANSYS, even like the student version, or there's other softwares that will give you trials. A lot of times, if you reach out to ANSYS or something like that, they will give your student team access to it, like specifically for the team. And also, I don't know if MUN has stuff in terms of that, But SolidWorks is okay for like basic structural simulations, like, okay, you have a beam here, and like a fixed contact point, but it's really not great when you get into any variable material properties where you're hardening something, or if it's carbon fiber, if it's composite. It's really not comprehensive in terms of that, and sometimes you'll get results that are completely inaccurate. So yeah, I would say if you can avoid SolidWorks for stuff like that, because that's what ended up happening. And then we went into SpaceX and they told us, your like, because you didn't harden this joint, the strength of the assembly, like the factor of safety is like, it was like, I think not even one at this point. So yeah, that's something to definitely watch out for, and also do some hand calcs to check everything out and make sure that you're setting up your simulation correctly, just as a sanity check.
Question from Kim. More often than not, it is tricky to find that sweet spot of reconciliation between being fast and efficient during design and being efficient in terms of machining time. How do you go about making such decisions as you go? Would it make sense to request an estimate for your labor costs?
That's going to depend on, in terms of machining time. So you'll kind of, the first part of that is you'll have to make a decision between like which components you're going to machine in-house, like either sourcing them to like the MUN shop or having students actually machine. And those things tend to be a little quicker, have a little more wiggle room, because if you order extra stock, you can do it again. And but if you have long lead components that you do not have the means to like machine in-house, it's definitely good to go to a manufacturer, kind of give them a vague, like, even if it's not the full drawing or the full design yet, show them like whatever 3D model you have at the time to show them, give them a vague idea of what's going on, and ask for, like, say, first of all, your student team, because that sometimes helps in terms of costs, especially because like if you put their name on your prototype or something, a lot of times they'll shoulder some of the cost and ask for a quote or an estimate, and ask for labor costs and stuff like that, but that should come on the quote as well. And yeah, that is tricky, and sometimes like you should also try to budget time for doing that, and then things not turning out quite how you expected, and probably having to send something back at some point.
Great. I hope that answers your question, Ken. Mariana, I had another question. So where you were trying to minimize weight with the design of the Hyperloop pod, were there any places where you had to make sacrifices for material properties in favor of weight?
Yes. Okay, so there was a lot that went into this, because we made material property sacrifices, but also like actual like physical component sacrifices at some points. And that was, I would say, actually less in terms of material properties, because once you decide what material you're going with, like most of the time we went with aluminum everywhere we could. There was barely any steel on the pod except for like bolts and stuff. That was pretty much it. And like couplings. But for the actual framing, we used exclusively aluminum, which is trickier to weld. That was part of the problem. And one recommendation there is, if you can afford it, T7075 instead of kind of like the standard machining grade like T6061 will give you a little bit more tensile and yield strength. And sometimes that's like just enough to, like, you can shave off a little more material there and stuff like that. But it is more expensive. And then in terms of, if you know your design well enough, there were components that we ended up taking off the pod or under designing, because if it was going to be used for like actual continuous use, you would not be able to remove those components, but you'd also have a bigger vehicle and like larger weight requirements. So we ended up actually removing a lot from the cooling system, because there was supposed to be an entire motor cooling system, and we ended up just filling it with the coolant DuXion 4. But we didn't have a cooling line because the run was so short that like we did the thermal simulation for that, and it didn't overheat in the runtime. Or the belts, for example, actually was not designed for the torque and RPM that we ran it at. But we contacted the manufacturer and said, is this like torque profile and based on testing where like it actually breaks at that point, or like since our use case is so short, can we use it for this application even though you wouldn't usually use it for that torque and RPM? So sometimes if you like have those calculations and you bring them to manufacturers, you can use things in a way that you wouldn't usually be able to, and it'll still be within the factor of safety if you properly like show your calculations and show like whatever simulation you use and stuff like that.
Well, getting creative with materials is cool.
What'd you say?
And you were getting creative with your materials, which is not something you see often, which is neat.
Oh yeah, I mean, I think it was good too, because then you get familiar with more materials and
So next question is from Iman. To what extent did you meet your timeline that you planned for the project? Specifically, when did you face unexpected results? From your experience, what advice would you give to others to avoid the delays?
So honestly, I don't think there was a single timeline that we hit. And I mean, I think that you'll see that pretty commonly for student teams, because everyone else I knew on student teams was similar. We were particularly bad for that because we had a pretty ambitious project scope and not a lot of time. And like some of the teams we were competing against were like working on it full time and had like millions of dollars in funding. But a lot of times, like, unless you're really lucky and happen to be at one of those schools, you're going to have to try to build as much time into your project so that like if you have like, okay, here's where the design part ends, here's like our critical design review, like give yourself a couple days or like some percentage of the project timeline after that, and basically just overestimate that by a few days or even weeks depending on how long the timeline is. And how big a milestone you're looking at. And I mean, I'd also say in terms of avoiding delays, like one thing that really comes to mind is tolerance and clearances. Like if you talk to a machinist, if you don't have someone on the team who's super experienced with that, talk to a machinist or talk to someone who's experienced with design for manufacturing to make sure that you're like first of all, dimensioning everything correctly and also tolerancing correctly, because like there's a specific like design practice for manufacturing drawings, and if you do that wrong, you'll confuse the manufacturer and you might either get parts back wrong or they'll send you back the drawing and say, I don't know what this means. But there's definitely resources to figure out how to do that properly, but that will save you a lot of time. And then another thing is organize your bolts and fittings and like really stay up to date on your bill of materials, because those things really creep up on you, and if you don't organize them, you'll end up like wasting money, because I guarantee you'll lose bolts and then you'll buy a couple and then you'll start being okay with buying more and more, and this is something that I was super guilty of. And yeah, it wastes time and money, and then people start like hoarding bolts because they don't want someone to take them, and it's bad. So yeah, organize your bolts, put them like in little cubbies or something and label them. Yeah, so those things like take up way more time than you'd think, and yeah.
So we're almost at time, so we're going to squeeze in one more question. Another one from Dr. Silva. If you can name one thing critical that you wish was covered in your school related to mechanical design, what would that be?
Oh, that's a really good question. I would say a lot more on, again, kind of what I was saying on that slide of, there are like material science courses, manufacturing courses, but if there is some type of course, maybe like, you know, kind of in the, I don't know what you guys call it at MUN, but like the general engineering, like introductory course, but for manufacturing, maybe where you actually not just conceptually look at like, okay, here's some material properties, but have to apply that and have to like practice designing for manufacturing in terms of like drawings and different types of materials. So not just your standard, like I think being on a team really pushed me to use like materials that you wouldn't usually use to save weight, and how that ties into simulation as well, because there's a lot of basic simulation, but when it gets into like there's kind of conceptual simulation, but also if you're doing it for manufacturing, I think there are some courses that will talk about composites or like talk about weld joints, but if you had one focused specifically on the elements of the design that you'll need to simulate for manufacturing.
A great answer. Thank you so much. So with that, we're over time. Thank you, everybody who tuned in today. So when you exit the meeting, it's going to automatically open up a survey for you to complete. It's not spam. If you can take a minute and fill that out for us, we'd really appreciate it. Stay up to date with us on Slack. Should be able to find us by searching, but if not, feel free to send me an email at kdoody at mun.ca, and we'll get you added. And we advertise for our events on there. You know, come see us soon. We're hoping to open up in the fall, and we're going to have lots of great facilities available to students. So thank you so much, everybody, for joining in, and we'll hope to see you next time.
Thank you.